attention, Mr. Chairman. Good afternoon. I'm afraid everyone is getting hungry. This is the final presentation in this session. Today I'd like to discuss the initial degradation, the crystallinity of the grain boundaries. So far, the global warming is a crucial issue for human beings all over the world. And this is one example of the carbon dioxide emission in Japan. So one-third of the carbon dioxide emission comes from the gas turbine system for energy power plants. Also, another 20% from transportation of gasoline engines. So, in order to minimize the carbon dioxide emission, easy answer is the elevation of the operating temperature from the viewpoint of thermal efficiency of our plants. So, the expected operating temperature, gas temperature, is the 1700 comparing with the conventional operating temperature. By elevating the operating temperature, we can improve the thermal efficiency of various power plants and chemical power plants by about 50%. Therefore, the increasing elevation of operating temperature is very easy answer from viewpoint of strength of materials. Of course, the elevation of temperature is crucial for decreasing the strength of the material. So, this is one example of the change in microtexture during creep test in nickel-based valley, which is the expected candidate for the various power plants at elevated temperature. This is the initial finely dispersed strengthened texture. It was called gamma prime phase, consists of eutectic phase of nickel-free aluminum. But during the creep test at 900 degrees C, you may see the initially finely dispersed microtexture is changed to the constant layer texture. Once this kind of layer texture appeared, flux starts to propagate and abrupt fracture occurred even in turbine blade. Similar change in microtexture has appeared even when the operating stress goes down to 250. This is the design stress for industry. 150 was the allowable maximum limit. So this is acceleration test, but even when the applied stress is one-third of the design structure, this kind of change in microtexture occurs. So before the creep fracture, this kind of change in microtexture occurred, and most of the lifetime of this nickel-based alloy is dominated by the change in microtexture. So the change of microtexture can be explained by the strain-induced anisotropic diffusion of component elements. So far, this is the very famous Fick's law, but all the chemists neglect the first part, divergent or diffusion constant. This is because so far the diffusion constant is assumed constant. Therefore, first term is neglected. However, when there is the distribution of diffusion constant in materials, this first term plays a very important role like this. Diffusion constant is accelerated by the gradient of stress in material. So far, the most simple expression for the stress-induced migration can be expressed by this equation. Here is the stress and V is expressed equivalent to volume. So the effective activation energy of diffusion is a strong function of local stress in the material, in structure. So therefore, the elevation of temperature here and increase in the operating stress accelerated the diffusion of component elements in the alloys. But unfortunately, diffusion constant of each element in the alloy should be different because of the difference in mass. Therefore, the local composition of the alloy should vary during the creep test. So, in addition to discuss the crystallinity, we assume the grain boundary should have some kind of volume from the viewpoint of diffusion along grain boundaries. So far the grain boundary is defined as the interface at which the crystallographic orientation is changed nearby two grains. However, there should be some kind of transition layer in between the viewpoint of strain, stress, and concentration of defects and impurities. Therefore, we can assume there should be some kind of volume like this, and by definition of this relative volume along grain boundaries, we can evaluate the crystallinity of not only grains, but also grain boundaries. So, in order to discuss crystallinity, the order of atom arrangement, we apply EBSD. So far, the electron beam is focused into the 50 nanometer, and we can scan the surface of the polycrystalline materials. And by analyzing the image quality and confidence index, we can define this kind of the area of each grain boundary. So, in order to discuss the order of atom arrangement, we applied image quality obtained from the analysis of the Kikichi pattern. So this Kikichi pattern is obtained from the result of interference of the reflected beam, and when the atomic configuration is periodic, we can obtain the strong sharpness of the Kikichi pattern. However, when the atomic configuration is random, like this, there are a lot of voids, defects in the area, the obtained Kikichi pattern is vague, so we can analyze the order of atom arrangement quantitatively by using this half transformation. And also we can detect the position of grain boundary, and this is the conventionally defined interface. By scanning the electron beam like this, we can obtain confidence index like this, and this is center position. But anyway, we can define the grain body region transition layer by using this confidence index. So by using these two parameters, we can map the crystallinity in the observed area, not only in grains but also grain boundaries. So first example is the evaluation of grave damage of nickel-based per alloy. Component of this CM247 LC is summarized by table, and mechanical properties of this material is like this, and this is great test condition. By changing the test time, we can obtain various fracture surface. And also we apply the Candle numbers misorientation like this. And this Km value is believed to have a strong relationship with the dislocation density. So when dislocation density increased, this Km value increased. So this is the change of Km value during the clip test. This is the initial value. It was the value, average value of this of the area is 0.1 degree. Surprisingly, this is a clip test. However, there is no drastic change in this Km value during the clip test. TL is the lifetime fracture, and T is the test time. So from 0.1 to 1.0, there is no change in the Km value. This means even the clip test on the fracture surface, dislocation density didn't change. If it is true, what causes the degradation of the material? So we observe change of image quality volume during the clip test. This is a black and white contour map, and you may be aware that the image changed to gray to black. This means this is the birth IQ value. It is clear the image quality value decreased during the clip test monotonically with testing time. So that means degradation of the order of atom arrangement occurred during the test. This is the summary of the change of image quality distribution of each sample as a function of testing time. This is the initial one, and 0.1, 0.2, 0.5, and 1.0. This is the final fracture. So this graph clearly indicates that the order of atom arrangement degraded during the creep test. But this degradation was not dominated by the increase in the distribution density. That means point defects mainly degraded the crystallinity of this alloy. So this result clearly indicates the change in microtexture was dominated by not the dislocations, but the anisotropic diffusion of component elements. In other words, point defects. Next, this is the next example of the alloy 670. It's also the nickel-based alloy. This is the final result of the inverse of fractal life versus the image quality. As you may see, the degradation occurred not only in grains, the mark area, but also the grain boundaries. So, therefore, also in this alloy 67, degradation was dominated by not the dislocations, but the anisotropic diffusion of component elements. So this IQ value is very effective for analyzing the degradation of the nickel-based superalloy quantitatively. Okay, this is the last example of a fatigue test of modified nichrome 1 molecular steel. And this is the chemical convention of this alloy. This alloy is expected for the candidate for the next nuclear power plant. So far, it was found that at high cycle fatigue test, fatigue limit disappear at temperatures higher than 500 degrees C. The expected operating temperature of this alloy is 550. Therefore, this appearance of this kind of fatigue limit is a crucial problem for industries. So we need to find out the reason for this appearance of the fatigue limit at elevated temperatures. So what we have found was that during the fatigue test, microtexture of this alloy also changed as a function of not only temperature, but also the amplitude of applied stress. The first axis indicates the amplitude of the fatigue test. In this test, the stress ratio was -1 by applying the rotating bending test. So what we have found was the initially dispersed last martensite microtexture disappeared during the test. And also the Km value decreased during the fatigue test as a function of the stress. So this result clearly indicates the recrystallization, recovery of the initial finely dispersed texture disappeared at elevated temperature under the application of some critical stress. This change in microtexture didn't dominated by temperature because the temperature of this sample is the same. So there should be some kind of critical stress at which the microtexture starts to change. So this is a summary of the degradation of image quality value during the fatigue test. There was the critical stress amplitude at 550 and 600, at which the microtexture start to change. So again, this image quality value is very effective for analyzing the degradation process of the microtexture in various alloys at elevated temperatures. This is a summary. So we propose new degradation materials under harsh environment, change the microtexture caused by the strain-induced anisotropic diffusion component elements. And new characterization parameter, image quality, was applied, obtained from the EBSD analysis. The observation of the degradation process during the grip and fatigue test of his resistance material showed this IQ value is very effective for analyzing the degradation process by not dislocations, but point effects. So quantitative analysis of the degradation of materials can be achieved by this image quality value. Okay, thank you for your kind attention.